Welcome to the educational research section of www.happynumbers.com. This video is dealing with a single case designs, and the particular design that we're going to look at in this video is called a multiple baseline design. Again, very briefly, remember, single case designs were developed to address the problem where we can't get large groups of a large sample together that we can assign people to an experimental group and control group and things like that. So a bunch of single case designs were developed, which are experimental designs, and they can establish experimental control and internal validity. I would recommend, if you have not already viewed, before you view this, I would recommend that you view the ABAB withdrawal design, because a bunch of vocabulary is explained there and discussed there. But let's take a look here at a multiple baseline single case design. Okay, the vocabulary: baseline condition, that is the initial condition where we start to collect data. Intervention, you know, that's the independent variable. Stability of data in terms of its slope and trend is very important. As discussed in the ABAB video, baseline logic: when a behavior stabilizes in terms of its level and its trend, we can assume that it has reached its natural level in the environment, and if there is no intervention, the behavior will stay at that level. And that assumption is called baseline logic. Internal validity, and that's the degree to which we can say it is the independent variable that has caused the change in the dependent variable. External validity, we had discussed that no one single case design in and of itself can be generalized, can establish external validity. However, if there is a preponderance of evidence, multiple replications over different subjects and things like that, and it's all leading the same way, we can start to build a sense of external validity. And time-lagged intervention. And this is a vocabulary term that is specific to multiple baseline and multiple probe designs. And rather than give you a definition now, we'll look at an example of it, and I think it'll become much clearer for you. All right, let's take this scenario. Let's suppose we're going to teach single-digit multiplication facts, and we have to a student, and we have 10 facts that we know the student does not know. And so that's, and this is the score: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, how many they get correct? This would be how many they get correct. And these are the different data collection sessions. So what we'll do is we'll take baseline data, and you'll see we have 3 baseline data points here. And the baseline data has stabilized in terms of level and trend, and so we can intervene, and bam, the data moves in a very therapeutic direction, and the student has reached criterion, has learned these single-digit multiplication facts. Well, we know this is an A-B design, and we know an A-B design is wonderful for a teacher, but it's not so wonderful for a researcher because it doesn't establish experimental control. So we cannot say with a great degree of probability that it was the intervention. So let's add another student. And so now we've taken baseline data for both students, and it's stable, and we can intervene, and the data moves in a therapeutic direction for both students. But the problem is, if this is an A-B design, and if this doesn't establish experimental control or internal validity, 2 of them are not going to establish it. So let's look at another scenario. So we had a third student, and we take baseline data. So we have baseline data for all 3 students. It's stable in terms of level and trend. We intervene. The data moves in all 3 tiers. These are called tiers, by the way. The data moves in all 3 tiers in a therapeutic direction. However, we have a series of 3 A-B designs, and we cannot say anything. There could be many confounding variables that has caused this to happen. So we could go on and on and on, but we're still not going to be able to make a case for internal validity. But let's take this scenario. We have a baseline, so we're going to take baseline data. Now we have 4 different students, and we're going to teach multiplication facts to these students. And we have a set of 10 multiplication facts for each student. They may be different for each student, and we're going to see the number that they can get right. And we're using an intervention called constant time delay, which is one of the earliest learning strategies. In fact, you might want to look that up on the internet. It's a very interesting and effective strategy for working with students. It reduces the number of errors to almost 0. Okay, well, so we've taken baseline data for all 4 students. Now, we intervene with the first student, and the data moves in a therapeutic direction. But we continued to take baseline data for the second, third, and fourth students, and their data has remained the same because we have not intervened there. So we've only intervened here with constant time delay. No intervention here, just baseline data, and just baseline data. These 3 have stayed stable, but when we use constant time delay in Tier 1, the data moved in a therapeutic direction. Now, suppose we now intervene in Tier 2 and see what happens. So we intervene in Tier 2, the data moves in a therapeutic direction, we continued to probe in Tier 1 and the data stayed at the criterion level. We took baseline data in Tier 3, it still was back at the original. We took baseline data in Tier 4, no interventions in 3 and 4, and it stayed down where it was. Now, we're going to intervene in Tier 3. Data moved in a therapeutic direction. We continued to probe in Tier 2 and the data stayed at criterion level. We continued to probe in Tier 1 and the data stayed at the criterion level. There has been no intervention in Tier 4 and the data was back at the original baseline level. Now we'll intervene in Tier 4. Data moves in a therapeutic direction. We continued to probe in Tier 3, the data stayed at criterion level. We continued to probe in Tier 2, it stays at criterion, and we continue to probe at Tier 1 and it stays at criterion. This is a multiple baseline design. Now, the time lag is this. We introduce the intervention here in sessions 5 to roughly 10, but we didn't introduce it here or here. Then we introduced the intervention into Tier 2 at around session 12 to around 22. Then we introduced the intervention in Tier 3 at around 22 to 30, and then we introduced in here around 30 to 31. So we staggered the intervention, and the fact that the data moves in a therapeutic direction only when we introduce the intervention into the tier. Notice that when we intervened here, this data stayed stable with no intervention. This stayed stable, this stayed stable. Then when we intervened in Tier 2, the data moved in a therapeutic direction, but the tiers where we didn't intervene stayed at stable level. That means that we can say with a high degree of probability that it was the independent variable, the strategy of constant time delay, that caused the change in the dependent variable, the number of multiplication facts that the student learned. Okay, now I know this is quite a lot, so let's go back and do a quick review. We take baseline data in all 4 tiers, and they're stable, so now we can intervene. We can assume if we don't do anything, baseline logic assumption will kick in, the data will remain the same. So we intervene in Tier 1, it moves in a therapeutic direction, we continue to collect baseline data, it continues to stay stable, it does not move. We then can intervene in Tier 2, The data in tier 2 moves in a therapeutic direction. We continue to probe in tier 1. It stays at criterion. Where we have no intervention, the data stays at the initial baseline level. The data has not moved. Then we go to tier 3. We intervene in tier 3. The data moves in a therapeutic direction. We continue to probe in tier 2. It stays at criterion. Tier 1, it stays at criterion. We continue to collect baseline data in tier 3. It has not moved. So now we can intervene in tier 4. It moves in a therapeutic direction to criterion. Tier 3, we continue to probe. It stays at criterion. Same with tier 2, same with tier 1. Therefore, since we've delayed the introduction of the interventions in each of the tiers, and the data has only moved in a therapeutic direction when we have intervened with constant time delay, we have made a very strong case for internal validity. All right, let's take a look at one that doesn't look so good. Here, first of all, the initial baseline data was not stable, so the researchers should not have intervened. And even though the data had moved in a therapeutic direction, down here, we're still in baseline condition, and this is very unstable. Here, very unstable, and we're in baseline condition, and here. So this particular one, this particular example, is a non-example of internal validity in a multiple baseline design. And the reason is that the data is all over the place in all of the baseline conditions. So baseline logic could not kick in. Okay, advantages. Very easy to use. Data collection and analysis, very simple. Excellent for classroom use. And it's very good for behaviors that are learned, that are non-reversible. One of the disadvantages that people can be in an extended baseline condition. That fourth tier, it wasn't until the 30th session that we introduced the intervention. So there's maybe some question about ethics of keeping someone in an extended baseline condition. The other thing is there are a lot of data points to be plotted here. This is a little more cumbersome than the AB design, but a very good design and excellent for classroom use. Okay, here's your assignment if you're working with me. Outline 2 classroom scenarios where you might use a multiple baseline design. What would the intervention or independent variable be? What would your data collection, what would you be collecting data on, your dependent variable? And then draw a hypothetical graph showing good internal validity and explain why. Well, thank you very much. We'll see you next time.